Good evening. Welcome to the Chatham Marconi Speaker Series. My name is Liz McCart and I'm a volunteer here. It is my privilege to welcome you to this program tonight and thank you for your support. As a reminder, you can pose your questions during the presentation by typing in the Q&A box, which is at the bottom of your screen. Type in your question and we'll answer as many questions as possible at the end of the program. We have all seen how wireless technology changes rapidly, including cellular service moving from 4G to 5G. What is dramatic is that this wireless technology is going to the moon. NASA is working on a communication and navigation network out of sight of Earth for astronauts to communicate back home. It's my privilege to welcome our speaker tonight, Dr. Eric Poole, who will talk about this amazing work. Dr. Poole is the Division Systems Engineer for Exploration and Space Communication at NASA Goddard Space Flight Center. Dr. Poole has a bachelor's in aerospace engineering from the University of Florida and a PhD from the University of Washington. After a brief time in West Palm Beach providing analysis of various rocket engines for Pratt & Whitney, Eric began his NASA career in Huntsville, Alabama, ensuring performance of the Space Shuttle solid rocket motors. He then returned to Florida, where he prepared such missions such as Juno, Curiosity, and Orion for launch from the Kennedy Space Center. He is currently a technical lead for NASA's communication and navigation systems, including the design of lunar networks in support of the Artemis missions. So Eric, welcome to our program tonight. We are very pleased to have you, and I will now turn the presentation over to you.
All right, thank you, everyone. First caveat, this is my first video presentation, so it's a little awkward for me because I can't see any of you and won't be getting any feedback. I will tell you my goal is to get through my slides in about a half hour. I like to have an interactive discussion with questions, but in this format, it's going to be a little different. So we'll save the questions till the end. I'm hoping you come up with a lot of them because frankly, the presentation is all stuff I know about it and it's stuff I work on. So to me, talking about it is work, but hearing from you and hearing your questions is where I kind of get energized. So I'm hoping you can come up with some good ones. First thing I'm going to do is start off with a pop quiz, and this will be a little different because I can't hear your answers, but we'll just take a moment. And the question I want to ask is, how many stars are in this picture? And normally I just let people shout out answers, but I think in this forum, I'll just give you a few minutes to think of your answer. And while you're working on that, don't worry, it won't be graded. So you can just come up with your own answers. I will share that at my work computer, this is my background, so that when I get a little in need of inspiration, I can stare off into the distance here.
So Eric, we do have some folks who are able to communicate with us, and I'm going to read you some answers.
Okay.
All right, so Bruce said 1.
Okay.
Ronald said cannot be determined.
Uh-huh.
Sarge says millions.
Okay, so Ruth is right. At least she's very close because this, I don't know if you can see my cursor, but in the lower right, there is a star symbol, the typical pattern you would see if you saw a star, and that's the one star you can see. I think there's really 3 because there's one just to the left of it, kind of hidden by a galaxy, and then one below that's a little questionable whether it's shining through a galaxy or not. But certainly Ruth is on the money there that most of what you're seeing are galaxies. And so you're not seeing any stars except for that one that's shining brightly, which means that, technically each of those blobs is tens of billions of stars, but really certainly at this resolution, you're not seeing stars, you're just seeing the collection of light coming from galaxies. And the thing about this, if, I don't know how many of you have heard, but these are called Hubble Deep Field images. And essentially, when the Hubble first went up, there was a scientist, and hold on, I need to turn something off here real quick. Uh-oh. Okay, won't be able to do that. All right, so what I was saying was there was a scientist who decided he wanted to look at a patch of the sky that didn't have anything in it. Basically because he wanted to see what was there. And there were people who had the opinion he was a little crazy to waste precious Hubble time on looking at nothing. But as you can see, if you stare at a patch of sky, you know, so this was collected over, I think it's days of collected time to get the brightness enough that you can make out these things. But this is essentially the least populated section of our sky. So looking at this, you can just imagine how much is really out there, and it's, you know, literally our brains are not really equipped to grasp it, but that's one of the things that fascinates me so much about space and why I went into this field in the first place. With that, a few more caveats. First of all, as mentioned in my short biography there, I'm really a rocket guy. Technically not a rocket scientist, I'm a rocket engineer. There are rocket scientists, they do fun things like, you know, thermonuclear engines and even antimatter drives and things like that. But most of us are rocket engineers, which is to say I have very little background about comm. So there are probably people in the audience who will be able to stump me about technical details of how communication systems work. But I will try to muddle through. I came into my job because I'm a systems engineer, which is a way of saying I know very little about a whole lot of subjects. So it's my job to kind of stitch things together. And so when we get into these charts, I stole them from a guy who's basically the father of LunaNet. And he was actually presenting this at an international conference this week. But I stole these charts so that if you see them pop up and they look way too technical and you're going to get bored, don't worry, I won't and can't delve into the details too much. I just wanted to give you a feel of what we're trying to do. So this is the top slide of what we're trying to do with LunaNet, and it's essentially just take something analogous to the internet to the moon. And the image there that we like to show is just think of astronaut with their tablet with little screens of where they are, local terrain, what the sun is doing at that time, maybe some data of science experiments that are nearby, and they would treat that connection, the wireless connection, back to all these sources of data just like we treat it here on Earth. They don't really know how it works. They don't care. They just know they're connected and they can get their data. That's essentially what we're trying to do. One thing I want to define, because it pops up later and not many people know about, is the difference between deep space and near space. So the official groups, the international groups that define these things, Space Frequency Coordination Group is one of them, defined it as 2 million kilometers from Earth. And even though most people do it, I'm trying to push that we use such things as gigameters. Certainly nobody talks about having 2 million kilobytes, right? You just say I have 2 gigabytes. Similarly, that's the beauty of the metric system. You can just, instead of having to talk about 2 and a bunch of zeros of kilometers, you can just say 2 gigameters. Anyway, that's how far away we cover here at Goddard. The deep space is covered by JPL. They run the deep space network, and here at Goddard, we run the near space network. And so the reason that's important is because Lunar is well within that range, and also the Sun-Earth Lagrange points 1 and 2. Those are popular places for spacecraft. Cell 1 is good for space weather alerts. So we have spacecraft that sit there, and for those of you who don't know, the Lagrange points are important because you can be far from Earth, but you never move relative to Earth. So they will always sit between the sun and the Earth. And then on the other side, James Webb Telescope, the new Roman telescope, there's a lot of telescopes going to Lagrange point 2 because they can get away from a lot of the influences of Earth, but still be close enough to talk back to us. And so we are setting up to communicate both with the moon and those Lagrange points. So just an overview, top level, of what the pieces of LunaNet are. So first there's the ground stations. You know, those are the things you can go visit. There's lots of dishes all around the world. The Deep Space Network has some of the largest in the world, and they have 3 sites, one in California, one in Australia, and one in Spain, that they're roughly equidistant around the world. And so we can always have an antenna in view of anything in the universe almost. So there's also plenty of other smaller dishes. There are commercial ones, and then there are government-owned. Lots of different networks. So that's your basis of how you get Earth down to the how you get data down to the ground. What we're setting up are all these what we call users, right? Our customers. So they would be the robots that fly to the South Pole. We're going to start with robots, of course. Land some at the South Pole. Viper is one that's going to go and do essentially some prospecting, digging in the soil there, the regolith, and looking for resources, mainly water. We're going to send a lot of spacecraft orbiting the moon. There are a few up there now. The Lunar Reconnaissance Orbiter is one that's been up for a long time. And then it gets more interesting when we start sending Gateway. It is a habitable, it's essentially a small space station that humans could go to. We're going to send it up empty first, and then later send the astronauts along in the Orion capsule as part of the Artemis program. So they would fly to Gateway, make a rendezvous, and then go down in the human landing system, which is under development now. So the key here is that if you're standing on the South Pole of the moon and you're trying to look at Earth, it's just like standing on the South Pole of Earth and trying to see the sun. Half the year, roughly, you can't see it. Well, a year in moon terms is 1 month. So for 2 weeks out of the month, the South Pole can see Earth, and 2 weeks it cannot. So we either have to land only when the South Pole is in view and conduct our mission and hurry back, or we have to have an orbital relay that can fly over and catch the signals coming up from the surface and then send it back to Earth. So we're, rather than trying to live with that restriction of only having half the time available, we're looking at setting up that relay to provide the continuous coverage of the South Pole. And then, of course, there's, if you look in the corner, there's these far side missions where we're going to land robots on the far side of the moon, just like the Chinese have done. And so there's no way, because the moon is tidal locked, the far side is always facing away from Earth. There's no way to talk to anyone over there unless you have a relay. So this is a chart that speaks to, you know, most people think of communications only, right? Everybody's pretty familiar with that. But this is just pointing out that if you set up these systems for communication, they can also provide other benefits. PNT services is one of the big ones. That's position, navigation, and timing, essentially telling spacecraft where they are and where they're going, which is obviously very important when you're in orbit, because if you don't know where you're going, you can mess up and not be in orbit anymore. So that's a very important thing for the spacecraft to know and to be able to get that data. And I'll talk more about that later. The detection services, essentially, you know, we have big antenna dishes, and they can detect solar flares, for instance, or other events of electromagnetic activity that are going on. Also very important when you're above the Earth's atmosphere, because you're not protected from radiation as you are here. So the astronauts need to know these things, and even spacecraft can readily be damaged and fail just due to radiation that they're facing out in the space environment. Again, once you get outside the atmosphere, you realize how much we are protected by that atmosphere. And then lastly, science services. Again, just think of radio astronomy. It's essentially a big giant dish. Some of the larger ones are used just for looking at radio signals coming from other stars and black holes and things like that. So if we have our dishes, we can similarly turn them on to receive those type of naturally occurring signals, not just the man-made signals. I also wanted to give you a little background about, and this will get a little bit long-winded, but the essence of DTN, delay tolerant networking, is that your normal IP that you use in your computers every day, you actually have to have a clear path between the source and the destination. And so essentially you type in the IP address, the computer looks around, finds the destination, and then when there's a clear path, it'll start sending the data. Well, the problem is if you get into kind of long distances, certainly long distances just due to travel of light, you start to violate the requirements for having an IP connection. And from here to Mars, for instance, you cannot use IP. But also, again, orbiting around the moon, if you get to the far side of the moon and you lose contact with the Earth, if you tried to establish an IP address, that wouldn't work. There's also, pointing problems. If you're pointing at, if the relay is pointing at the surface, sometimes it can't always simultaneously point at Earth, so it can't provide that continuous path. So what they came up with is a protocol called DTN. And essentially it's just, if there's a node that the data can move to, all the packets are transferred, and then it waits until it can transfer again. And so the diagram there is kind of showing you this graphically why that's so beneficial. The reason I bring it up, and I'll probably touch on it in later charts, is this gets to the whole point, or not the whole point, but one of the big points of going to the moon is to learn things about going to Mars and kind of break ourselves of habits that we've developed in operating in LEO or low Earth orbit, where the space station is now. At the moon, you can kind of get away with using IP, but there are also times when it's better to use DTN. So the idea is it's a perfect example of, again, trying to wean ourselves from dependency on Earth by developing these technologies and capabilities that will work for us on Mars or other planetary bodies. Personally, I'm pushing for Venus. I think it's a more interesting destination, but we still need to work on quite a few things before we're capable of pulling off a stunt like that. And here we get into, again, I'm not going to dive into this. This is a little more academic, but you can start to see, obviously we're trying to contact the Earth. We're looking at sources of information on the surface. We've got our relays that we're using. There's other users. The orbiting gateway is kind of both user and node, as we call it. So it can contribute to the network and receive information from users and then turn it around and send it back to Earth. But it also generates its own data. Obviously, when the astronauts are in there, we have to service them, and they will be generating lots of data that we need to get down. And then visiting vehicles, so that would be the Orion capsule. If it leaves Earth, it'll come and visit the gateway. And so there are maneuvers when it's in close proximity. And so it's actually much closer to a wireless system that they have in place for those kind of prox ops, proximity operations. I did want to touch on the PNT. So that these are fairly old charts that we use to talk about the space network, which has been around a long time. But I thought this was good just to give you an idea of how we do this. And it's essentially to talk to a spacecraft. You do have, depending on the frequency of the signal you're sending, you can get a different size field of view, if you will. So the cone essentially of the signal. And if you're outside of that cone, you don't pick up the signal. If you're in the dead center, you get the full strength of the signal. So essentially, we have to have very accurate pointing when we're talking to spacecraft. So the spacecraft in the middle is actually a TDRS, telemetry and data relay satellite that we use, and these are geostationary. So they're in orbit at fixed longitudes, and we have our ground stations that talk to them. So we are very precise. They do move around a little bit, but we can track them very well. But the main thing is in the user spacecraft, which is on the right there. That's the one that we have to get very good tracking information so we can point those antennas in the TDRS at the spacecraft and get a good strong signal. So since we're doing all that just to communicate, we can essentially take that data and embed it in a message that goes to the spacecraft that tells them, hey, when we contacted you, we were pointing here. So that means you're somewhere in this neighborhood. And then the spacecraft use that. Obviously, a lot of them are using GPS now, but some of them also like to get this as a backup because sometimes the GPS systems fail or they're having problems. And this way they can still get good data about where their spacecraft is. Ranging is yeah, you just embed the codes, and then you determine through the speed of light how long it took that code to reach you. Essentially, a code is just it's a series of characters, if you will, that are very long strings, and I don't have the numbers off the top of my head, but if you can determine where the start of the signal is and the end of the signal, it's actually many kilometers long. So when I say it's a long signal, it really is. But when you receive it, then you can get very good definition, because it's so long, of when the code got to you, you know precisely when it left the other spacecraft and when it got to you. And you can use that time to tell exactly, down to meters, how far away you are. And by the way, I don't get into the optics much, but we have now optical systems. And if you use optometrics, which is the same thing with light, you can get down to centimeter resolution of how far these spacecraft are from each other. And then the last thing is the Doppler compensation. So this takes advantage of the Doppler effect. We simply send a signal with a known frequency, and based on the Doppler shift that comes to the receiving spacecraft, you can determine the relative velocity between the two spacecraft to a very fine precision. Can't remember why I had this in here, but it's probably more detailed than you want. Just to say that, yeah, it's not as simple as it sounds. There's a lot that goes into determining what's on, each spacecraft, what's on the ground station, how these numbers are calculated and then computed, and where that's computed even. Again, these days, the philosophy is do as little on the spacecraft as you can. Just get the data down and we'll figure things out on the ground. Shifting to, a Mars forward, as we call it, operations around the moon, we want to sever our ties with the ground. So we are trying to shift more autonomy, more computation to the spacecraft itself, so that it doesn't have to, send its data down to Earth, wait for Earth to figure things out, send up the commands, and you get that delay. When you're operating in low Earth orbit, it's not so bad, but when you're operating on the moon, or especially Mars, you can't be dependent on the ground for doing all this thinking for the spacecraft. Again, another one, this was kind of intentionally, it gets complicated trying to keep track of all these elements. And, frankly, at the moon, this is light compared to what we normally do on Earth. So that's part of why they need people like me. My specialty is in figuring out the process for keeping track of all these pieces, and not necessarily understanding the individual pieces as well as a lot of people I work with, but in understanding the system of how we keep track of what all these needs are and how we will meet them. And this is kind of how it builds up. What we're working on right now is pretty simple. We are looking at building, as it says, one or more relays ourselves. We'd like to have 3. That would be ideal, because then you get full coverage. 1 is obviously pretty helpful. You can get up to 95% coverage that way. But that's what NASA would be producing. ESA is also looking at putting something up there. And then, as I've said, Gateway is going to be there, and it can act as a node itself. So right now, our whole constellation that we're looking at is, depending on exactly when you're talking about and when spacecraft are able to be built, 1 to 5 in the beginning. And the users we're servicing are similarly, there's not too many that are planned in the early years up through 24, 25 timeframe. We're expecting, 1 HLS mission of 10 days or so. HLS is, acronyms are going to spill in once in a while. That's the human landing system that's going to put humans on the surface of the moon. So that's obviously the big one that we have to be very careful that we build very robust systems to make sure the astronauts are okay. But then there'll be a few robotic landers and CubeSats, as we call them. They're small, literally like this size cubes, satellites that get set up that will go along with other missions. We very rarely will launch a rocket just for the CubeSats, but they're very easy to put on other rockets that are going up anyway. And so we've gotten into the habit of doing that. We call it a ride share, right? So they're just hitching a ride on somebody else's rocket, but we'll put some of them up as well. So the user community is pretty small. as we build up into 28, we have plans on the drawing board right now that in the 28 and on timeframe, it gets pretty crowded. You know, we end up with multiple human landing missions. We have lots of rovers running around on the surface. We have lots of CubeSats and even larger spacecraft running around it. And so our focus is on the near term, obviously, making sure we pull off the initial steps, but we're mindful that what we build today can be built up into a more complex network. And that's kind of the whole point behind LunaNet. It would be easy to just say, all right, we have this spacecraft that needs to talk to this relay, which talks to this one ground station. But it's developing the standards that everyone can live by. That's kind of hard. Think of any, you know, new technology that came along. There were different standards that would be competed. Think VHS and beta, that sort of thing. And so we're kind of in that mode where there's people in different camps who want to build satellites that wouldn't be able to talk to each other, essentially. And so we're trying to think ahead and say, you know, we can't add that complexity to our network. We need it like the internet is today, where you hook any computer into another computer and it can talk to it, right? We want that kind of plug and play. And so that's what we're working on right now. And my last slide, again, just kind of summing up, LunaNet is the idea that, hey, you know, we're starting off small. We just have a few nodes. We could do a lot of different things, but we want to think ahead. We want to think ahead, you know, not only to a full lunar base with lots of users, lots of providers. You know, again, I didn't really stress it, but we, NASA are looking at building a few pieces of this puzzle. We are inviting industry, commercial companies to provide pieces that can answer this and be like your cell phone service where they just offer you a pay by the minute type service. We're trying to see if we can help them establish that. We'd rather do it that way than have to build it ourselves. We have international partners. ESA is very interested in doing this. And they have a couple proposals on the board specifically for a lunar relay. So we're talking to them. We know if this really kicks off, all those are going to be there, right? There's going to be industry, there's going to be international partners, there's going to be NASA. So we have to work together, and we're trying to set up to be able to do that seamlessly between, you know, lots of different organizations. Also trying to get the evolution straight. We can't afford to provide the final, you know, infrastructure. It has to be like any frontier is developed. You establish a few trails, and then you build up, you know, trading posts, and then roads, and then the infrastructure follows the commerce, if you will. And so there's only going to be a few customers to start off, and so the infrastructure will be small. If it evolves the way we hope it will, then the infrastructure needs will grow, and we'll just grow. We'll develop a process for evaluating how much infrastructure we need and providing just that much as it builds up over time. And then the main thing is, or one of the big things is, if we can pull this off and get it set up right, we will know exactly what we need to do to go to Mars, or again, any destination that we choose in the future. If some of you have been following space, you know, there's been, hey, let's go to the moon. Hey, let's go to Mars. Hey, let's go to an asteroid, and back and forth. But NASA has become savvy at saying, you know what, we're going to develop the capability, and if the destination changes, we don't have to throw away what we learned and start over. So that's what we're doing here. You know, the administrations have changed, which means our leadership has changed, but we've been able to, since Constellation, been able to pretty much stay on course with what we've been trying to do, and show that, hey, you know, NASA's ready no matter where you want to go. We're building for being a spacefaring nation, and it's not destination dependent. So with that, I will end the show. And I actually did hit my mark, so we have plenty of time for questions, and I will open it up to Liz.
Okay, thank you, Eric. That is amazing technology, to say the least. And it must be interesting to work on that day to day, as well as work with your partners. So it is time for a Q&A. So if anyone has a question, and we already have some for you, you can type it into the Q&A box, which is at the bottom of the screen. One thing that we always like to ask, Eric, is what would you recommend in terms of reading, like websites or books or further resources? Do you have some specific recommendations? I'm sure there's plenty of materials out there.
There are a lot of materials out there. And I do remember, yeah, I was supposed to get specific ones for you and I failed to do my homework. There's actually and I'll make this available. I can probably do it right after this meeting, but I get a notice, or I get an email that has a kind of a summary of everything interesting going on with space. So that's delivered to my inbox, and I highly recommend that. I haven't had time in the last, I don't know, 4 months to read it because it's been pretty hectic at work with what I've been talking about. But I have in the past tried to make it a good practice, and it is surprising because NASA is so big. I learned things through that I should have learned, by talking to the person down the hall when we were in the office. But yeah, it's very helpful. So I can share that with the group as soon as we get done here.
Okay, that would be great. So if you want to send that to me, then we can distribute it to the viewers that participated today. Thank you. So we do have some questions. Tom would like to know, why choose the lunar South Pole? Why not the North Pole?
So the main reason is the North Pole has fewer resources and is even worse terrain. When the Apollo astronauts went up, they landed in the easiest areas to land to start with, certainly Apollo 11. They landed in a nice flat spot. The problem with both poles is that they're pretty mountainous. So it's hard to find places that are both interesting, and by that we mean permanently shadowed. The permanently shadowed regions are where the water is because it hasn't boiled off. Obviously, the sun never shines on it, so it's really cold and it captures the water. But obviously, those are the hardest regions to land in and travel through. It's just like landing in a mountain range. So the South Pole is slightly better. It's got bigger craters and less mountains. So that's kind of why we're going that way.
All right, thank you for that. A viewer, Liz, would like to know, are other countries involved in this effort?
Yes, definitely. So they're involved across the board. I'll just speak with communication. Again, the first part of LunaNet probably is going to be something called Pathfinder. It's actually a company called Surrey. I forget their full name, but they essentially work for ESA, the European Space Agency, and they are busily building, or designing anyway, a relay satellite that would be good for the CLPS missions, we call them, the commercial lunar payload. I'm sorry, I don't have the acronym, but it's essentially, we put out a commercial bid. Anyone could bid on it, and I think we had a dozen companies that were awarded to provide service to, essentially, NASA would hand them a scientific payload, and they were responsible, we'd hand our payload to them, and they were responsible for getting it on the surface of the moon. So they have easier communications requirements than the humans do, obviously. So Pathfinder is probably, it's a smaller relay satellite, but it's capable of providing that. And we are in discussions with them like almost daily between NASA and especially the CLPS program to work out the details of how that service would work. From a larger perspective, the one I'm working on for the larger capability for the human landing system, Thales is working that, Alenia Aerospace. There's kind of a group of people, so they're mostly in Italy. They are, anytime you talk to really any company or organization in space, they have, it's a team, right? There's very few that go it alone. So it's really a consortium that's working for ESA there. But it's not just ESA. We work with Canada all the time, even though technically they're part of ESA. Yes, Canada is part of the European Space Agency, but we also work with them independently, which is interesting. And then, of course, Australia, because we need especially with us in the communications business, because we need that land site on the other side of the world, Australia happens to be a good spot. We work with them all the time in the communications business. So the Australian Space Agency is another one. There are, I don't even know how many countries, Brazil has a pretty robust space agency, and they all want to be part of it. They want NASA to lead because we have the most money and the best resources, but they all want to be part of it because, it's cool.
It is very cool. You're absolutely right. So actually, Melissa had a question about ESA. So I think you've explained that a bit, that ESA is the European Space Agency.
Yes.
Yeah. Do you would you expand on that a little bit? So
European Space Agency, anytime, as we've said, anybody who feels bad about the bureaucracy of working with NASA should try working with ESA. It's essentially a group of, and again, it's somewhere in the teens, number of countries. So most of the European countries, of course, France, Germany, Italy, England, those are the big ones in there. But what they do is their governments give a certain pot of money into ESA. There's a central organization that runs it, and they allocate space missions back to the countries, the work of working on space missions back to the countries that contributed in the same proportion. So it's a very complex system, but they essentially are an equivalent of NASA, where they launch their own missions to various places in the solar system. They have their own communications network where they have dishes around the world and they can track their satellites. And so we do have partnerships where sometimes we use their systems, they use ours, we back each other up. So yeah, it's the European version of NASA.
okay, thanks. That was helpful. So it's sort of a follow up from Dick. So LunaNet will be available to other countries. That's part of the collaboration.
Yes, that is the intent, is to make it available to anyone who's going there. It's again, because it's a coalition of the willing, I guess you would say. We can't enforce it, right? But it would be available, and of course the question becomes a matter of funding, right? If you're going to use the system, you would be expected to contribute to the funding of the system, and so. Fortunately, I'm not in the budget side, so that's less my problem. But from a technical perspective, that's why, again, we're pushing for what we call interoperability, right? Anybody can operate with any other piece of the system, but we have to get agreement on the standards. And so that's the hardest part right now, because everybody has their little flavor of, well, it's essentially what happens is you get a bunch of engineers and they want to optimize. Right, and they have their different views of what optimal means. And if you tweak it this way, it's a little better for doing this. But if you tweak it that way, it's a little better for doing this. And so nobody agrees on exactly how to do it, where you say, okay, if we just realize it's going to be not quite optimal, but we can find a common ground, then we can all work together. And overall, it's better for everyone.
Okay, thanks. So we have a couple questions. Rich and Tom are curious about the Chinese. The Chinese landed on the far side of the moon. How do they communicate? And is NASA talking to them about LunaNet?
No, we are not allowed to. It's by federal law that we are not allowed to work with the Chinese. But the way they do it, and I think it's, I'm going to mess up the Chinese name, but they have a relay satellite at Earth Moon L2. So we've looked at that. We don't really like, I think it's Bedu, but I may be mixing that up with another mission. Anyway, yeah, it's at Earth Moon L2. We don't really like that because it's pretty far away from the surface of the moon. It is good if you're only on the far side because you get 24/7 coverage, right? It's parked on the far side of the moon or looking down on the far side of the moon. So they don't have to worry about blackouts when you're in orbit, and you can get much closer to the surface, which means, of course, better communication, right? I mean, that's pretty straightforward. If you're too far away from the cell tower, you lose your signal. It's the same way in space. If you get too far away from the user, you lose the signal, or you have to build a really big radio with lots of power. So that was the drawback. And we're looking at orbits around the moon. You do lose coverage for a few hours, but you can play games with the elliptical orbits. So you're mostly above the South Pole, and you only have quick passes over the North Pole, and then you're back in view. And the NRHO, the near rectilinear halo orbit, that's where Gateway, and we've looked at using that. It's like a super elliptical orbit where I think it's 6 days you're over the South Pole, and you go really far out. You go 70 kilometers, or I'm sorry, 70,000 kilometers. Again, 70 megameters is easier for me to remember, away from the surface of the pole. So again, you pay that sacrifice of being distant, and you're, if you're in a closer elliptical orbit, you can get around 6.5 megameters, so factor of 10. And since power is basically on area, you get a factor of 100 dB loss if you get out to the end of the NRHO orbit. But on the plus side, you get better coverage. So, we're weighing those things.
Okay, thank you. Dick would like to say fantastic program. Thank you.
Thank you.
Okay. Melissa and Bill would like to know, why is Venus of more interest to you than Mars?
I guess we know a lot about Mars. It's kind of a dusty place. There may be evidence that there was life, even possibly, some microbial life hidden away somewhere below the surface. But it's kind of it's a well-known commodity and doesn't have, don't see as much potential there. Whereas Venus, we know very little about. And now that we've kind of figured out, as long as you don't go to the surface, it's easy to establish an outpost in the upper atmosphere. And we could fairly easily build a, research center in essentially a dirigible that floats permanently above the surface, and then learn a lot about Venus. It's very dynamic. It also, we could probably learn a lot about the greenhouse effect, because there is theories that one day, briefly, Venus was like Earth, and then the greenhouse effect took over, and you got what you have today, which is, nothing. Life as we know it certainly cannot exist there. It's brutal on the surface. Robots have a hard time. I think we've only, had minutes of life on the landers we've sent down there, which again is another reason to go explore, because we know so little about it. And it's hard to see down there because the atmosphere is so thick. You don't even really know what the surface looks like. There's just lots to find out if you go there.
Great, thank you. A viewer, Liz, would like to know, when do you think astronauts on the moon will use LunaNet?
Well, before they even touch down, right? We're going to have LunaNet established well before the astronauts even take off, because we want to make sure the system is up and working. And so we'll have test missions. We're trying to plan that, not have the system stood up right before they get there, but have it several missions before that so we can check it out. So essentially, once they leave, get above GEO, well, I guess it might not be until they get to transit all the way to the moon, but certainly when they get in the proximity of the moon, they would be using our LunaNet resources rather than the typical ground stations that support the space station right now.
And then I think you mentioned, so that system would be in place in 2024. Is that the target?
Yeah, currently our first landing is targeted for 2024. So we are trying to get this established by 23, which is going to be tough, but that's what we're trying to do right now.
Feels right around the corner, doesn't it?
Yeah.
Yeah. Peter would like to know whether there will be any type of encryption technology used to secure these links. Are they open, standard, or government proprietary?
So, I'm getting a little bit out of my depth, but basically all commanding to spacecraft Certainly around the Earth are encrypted simply because, well, the doomsday scenario is somebody hacks it and sends a command to crash it into a populated area. So we are very serious. We have people, that's their full-time job, to keep up on the encryptions and make sure no one could ever break into commanding one of our spacecraft. And even when spacecraft leave, frankly, we don't want anybody playing with our toys. So we're very careful about encrypting our uplink. The downlink, it's not so critical. Most of this is publicly shared scientific data. Certainly some of the human stuff we will encrypt. But I guess I would say we're very close friends with NIST, the National Institute of Standards and Technology. It's right down the street from us here at Goddard, and they are in charge of all encryption for the government, and we work closely with them. And so we keep pretty good tabs on our encryption capabilities. And so we have the latest and we use it.
Okay, thank you. And we're getting to the final question here. So you mentioned commercial partners. And how does that work? What kind of partners do you have, and what's their role?
Well, the two, I'll list two big ones right now is KSAT, and I'm sorry, I'm blanking on the other name. It'll come to me. But anyway, these are companies who stood themselves up, and government is just one of their customers, right? There are plenty of other spacecraft up in space that need communication. So they have dishes all around the world, and we pay them by the pass. I'll just throw a number out there. Obviously, accounting is a little more complicated, but if one of our spacecraft flies over, say, the South Pole, there's a station called Troll in Antarctica where the reason we like the poles is because we have a lot of polar orbiting spacecraft, and you pass the poles every orbit, right? Each pole every orbit. So if you put a station on the pole, you can pretty much hit that station almost every orbit. So we have spacecraft in Leo. In Leo, you pass over a spot on the Earth that you can see with a radio for about 10 minutes at a time. It's a very limited view because you're in so close. But for one of those 10-minute passes, we'll pay them about like $500. And so, it's an automated system. We have a schedule that comes out weeks in advance. It says, hey, yeah, we're flying over you. We want to pick up a pass, point your dish at us. And they say, okay, they schedule it up. They pick up the spacecraft as it comes over the horizon, lock onto it, pick up the data as it goes. They pass the data to us, and we pay them the money, and there you go. It's a service. So that's the kind of thing that we already have in existence right now. We're looking to expand more on that because we do still own a lot of stations in places where the commercial side hasn't picked up yet, but we're pushing companies and telling them, hey, we'll give you money if you provide the service for us. So, and they're responding. So we're working to up that commercial side of it so that we can, just like we did with the rocket launches, SpaceX is the famous one. Originally we owned a lot of that, and now we just pay for the ride, right? We say, hey, deliver our cargo to space station, and we'll just pay you for delivery instead of managing it ourselves. And that's frankly free. It's gotten cheaper, which is why you go to commercial, because they're all about cutting their costs and making money. And the way they do that is, again, finding ways to cut corners. Government's not good at doing that. So we turned it over to the commercial guys, and they found ways to cut corners and still provide the service we asked them to. And that's freed up our budgets to go do more exciting stuff. So we're looking to do the same thing with some of our communications. Obviously, there's not a whole lot of infrastructure at the moon. And so it's a little tougher to say we're going to commercialize it, but someday we'll just keep expanding our commercial base until it gets there.
No, thank you. It's an interesting combination of government and industry to go to the moon, literally. Yeah, great. Well, Eric, thank you so much for this presentation. It was very interesting. I think we'll be researching more and looking at the information that you send to me that I will get out to people, and we'll keep watching NASA for what you do next. So as a small token of our appreciation, we are going to send you this Chatham Marconi Maritime hat. So I'll get your address from you. And certainly if you're ever up this way, please stop in. We'd love to see you. And just a quick note for our members, we are pleased to be open at the museum. As we did last year, you can reserve a spot on the website. We have some new exhibits, so we'd look forward to seeing you over the season. So thank you all. Thank you again, Eric. We appreciate your time.
My pleasure.
And we'll see you soon. Thank you and good night.
Good night.